Hey guys, it's a second order low pass filter with a Butterworth response, and we'll come across like obtaining the transfer. We'll be asked to derive the transfer function, and during this procedure itself we will come across the design part also. Like at a point we'll obtain the transfer function, and at a point that gives us, let's do, and it's a little bit incomplete. That incomplete is this one. This we'll have a feedback connected over here. Please don't forget that one. And another point to be remembered is the op amp is in non-inverting. Input is given to the non-inverting terminal. So usually V0 will be equal to 1 plus RF by R1 into Vn. So this is what happens. But here in this configuration, Vn is not directly given to the non-inverting terminal, so we'll have to do a small analysis. In the sense, let's assume that the drop across this capacitor is V1 and the drop across this capacitor is VA. Now VA is given as input to the operational amplifier. For this reason, this takes the form V0 equal to this one, writing it as AF, it will be VA. We'll have to find out this one, like VA. We need to derive the expression for VA and then plug in over there. That itself we'll be having V0 and Vin, and then getting back to that one. So here, and another point is we have current I1. Let's say I1 is flowing up to this point. After this node, that splits into current I2, all right, and I3 this way. Why not into the operational amplifier? Why? Because the op amp input impedance is very high, so this current is almost negligible. Total current will be flowing in this direction, all right. And for the analysis part, we don't need this anymore. So guys, this one V0 will be appearing over here. See the connection, V0 will be appearing over there. So in that way, we don't need this, and here V0 will be here. V0 comes over here with that small change, and this network is enough to obtain that expression for VA. And here we have I1 splits into I2 and I3. So what can we write from that? This arrangement, I1, current I1 equals I2 plus I3. Making use of node analysis, we'll have to write the expression for I1. I1 is here between Vin and V1 upon R2. This one, from this part, from here to here, I1 can be written as Vin minus V1 upon R2, that which equals I2. I2 is here. Right, so from this point to this point, we have V1 minus V0 upon the capacitive reactance. It's not C2, but the reactance, that is 1 upon SC2. Where did we get this one from? The capacitive reactance is XC, that is equal to 1 by J omega C. This J omega is written with the S for our convenience. Why to write that J omega again and again? No, like reducing, it should be in terms of S, so that we can have a standard comparison for a second order system. That's it. And this is for I2 plus I3 from this point to this point between V1 and VA upon R3. So V1 minus VA upon R3 will be that for I3. And after this, we'll have to, like, we have a potential, we need to apply some potential divider rule across this part, across this part. So from here, VA, from this very arrangement, VA can be written as the supply V1 into 1 by SC3, the capacitive reactance, by total impedance, it's a R3 plus 1 by SC3. Simplifying this one, absolutely VA will be equal to V1 upon 1 plus SR3 C3. You just do it. Let's simplify this one, and the denominators in the numerator and denominator gets cancelled, and finally we'll be reaching over there. Alright, from this expression we have V1 is equal to 1 plus S R3 C3 times VA. Now what to do with this one, this expression plugging in over here, we will make sure V1 doesn't exist anymore, and the entire expression will be in terms of Vin, V0 and VA, which is useful for us to derive the transfer function. Alright, so in that way how to write this expression gets converted to here Vn. In place of V1 we'll plug in this one. Alright, 1 plus S R3 C3 times VA entirely upon R2, and in that second expression also in terms of V1 we'll have to plug in 1 plus S R3 C3 times VA minus V0, and this one it's 1 upon SC2 that gets multiplied with entire term like this one SC2. Please make a note of this change, plus even in this V1 we need to plug in this one. What is that? 1 plus S R3 C3 times VA. Alright, in terms of V1 we have another VA minus VA upon entirely upon R3. This is the arrangement. The equation takes the form with V1 plugging in V1. Alright, so here we need to find the expression for VA so that we can plug in over here. So in that case, rearranging this equation in such a way that terms associated with VA on one half and terms independent of VA on another half. So we have this one, see this Vin by R2 as it is, Vin upon R2 as it is, and look carefully here, this is independent of VA, which is multiplied with S into C2, which is negative while it is in RHS, and pulling it to LHS that will be positive. So we have plus V0 into SC2. Alright, so we'll have to drag this one to that side, this by this to that one, so that we can make sure that VA terms are all we have that VA terms on one half completely. Alright, so watch carefully, we don't have this anymore, this one is multiplied with this one, that's okay. Each and every term we have VA. Alright, from here we can take out VA as common, even from here we can take VA as common. VA, even after dragging this to RHS we can take out VA as common, so taking to make it even more smaller, that expression even more clear, so open a big bracket, saying that we have VA multiplied with all this one. Okay. So this repeats as it is, which is multiplied with this one. It's taking out, guys, it's negative to that side, that will be positive. Taking out 1 plus S R3 C3 as common from this and this one also, it will be positive. Remember this will be positive. So in that way, open another bracket to say that this is taken out, only this is left. SC2 is left from here. Alright, so let me remove it so that I don't get confused. This is done, right? And even here this and this is over here, this is over here, so 1 plus 1 upon R3 is left over, and when this is pulled that side, this is taken out, it is negative this side, going that side it will be positive, and only 1 by R2 will be left over. So close the braces. Here says that this is the one, minus we are left with another term, minus VA is pulled out over here, so we are left with 1 by R3. So to make sure this entirely this one, right? So this complete, all the terms are multiplied with VA. Another simplification over here, guys, another simplification over here itself, upon R2 into R2. I have, this is clear, done. So still simplifying this one, simplifying inside the braces, that this one, simplifying this one, what do we have, guys, this one, RHS, it's a VA multiplied, all right. So 1 plus S R3 C3 inside the braces as it is. Now here let's take another simplification over here. Like here we have by 1, isn't it? So LCM, it will be entirely LCM, it will be R2 R3, and in that case this gets multiplied, S C2 gets multiplied with R2 R3 plus this gets multiplied with R2 plus this gets multiplied with R3, close the braces, minus 1 upon R3 complete braces between this and this. And another simplification is that VA still as it is, this braces 1 plus S R3 C3 also into S C2 R2 R3 plus R2 plus R3 bracket close upon R2 R3 minus this. If this is simplified, if this is one term and this is another term, isn't it? If this is simplified, we'll have R2 appearing over here, we can close the braces. On LHS, what do we have? We have VN plus V0 into S C2 R2 upon R2. Something gets cancelled on either side. Check, watch carefully. Here, I guess R2 gets cancelled on either side. Here, this R2 and this R2, because all the terms are in the numerator and that's the common denominator. So we don't have this R2 anymore, no R2 anymore. All right. And one more small modification is that let's do this one. Let's do this one, that here into R3, which is equal to this one, so that we don't need this one. We can erase this one, R3 multiplying over that side. All right. So let it be this small simplification in the RHS. VA is still existing in the same way, guys. Multiplying this one, this term and this term, 1 multiplied with this term, so this entire expression repeats in the sense S C2 R2 R3 plus R2 plus R3, and this term gets multiplied with 1, 2 and 3. So plus this into this, we have S square R2 R3 C2 C3 and another R3, isn't it? R2 R3 C2 C3 1, 2, 3, 4 and another R3. Hope it's clear. And this one, when multiplied with this one, this S R3 C3 gets multiplied with R2 plus one more term, this S R3 C3 gets multiplied with another R3 over here, R3. That's it. Opening, simplifying these two, and we have minus R2. So from we can close the braces. All right. From this end to that end, something gets cancelled over here. Guys, check carefully. Here we have plus R2 and we have minus R2. That doesn't exist anymore. We can remove this term. This can be removed. We can close the braces over here. And watch carefully, we have R3 in each and every term extra. So R3 from here, R3 from here, another R3, second R3 from here, R3 from here, and second R3 from here can be taken out, isn't it? So with that one we have, if that R3 is taken out, we don't have this anymore, and this will be 1, this will be 1, and this second R3 we don't have here, that doesn't exist anymore, and this R3 also doesn't exist anymore, and here we don't have that R3 also. All right, so this is a simplification. Over this side we have this one, in the sense R3 on either side gets cancelled. Okay, this is the LH part till I didn't touch it, and this is the RHS part when simplified, and on either side we have R3 which doesn't exist anymore. We can remove this R3 entirely on either side also. Here this one which equals this one, right? And here we have VA left over, and from this one, from this very expression, we have VN plus V naught S C2 R2 upon this entire expression, and it's S square R2 R3 C2 C3 plus S into, here taking out, we have S has come from here, this doesn't exist anymore, let me remove that so that it will be clear for me. S over here, so taking out S as common, we have R2 C2 from here and R3 C3 from that one plus R3 C3 from this one, and it's a S has come out, so we have plus R2 C3 from that term, close the braces, and it's plus 1. 1 is over here, and yeah, this is the simplification, that which equals VA. Now we have the expression for VA in terms of V in and V naught here itself. Once again, we'll have to get back to that expression which I've told you at the beginning. What is that? V naught is gain times VA, where VA is the input to the operational amplifier. So we have V naught equals AF VA. Alright, AF is nothing but 1 plus RF by R1 according to that analysis which we have done for non-inverting amplifier. And this one, so entire this expression to be plugged in over here. Alright, so what is VA? It's like braces, V in plus V naught into S C2 R2 repeats as it is upon, what do we have? It's a S square R2 R3 C2 C3 plus S times R2 R2 C2 plus R3 C3 plus R2 C3, close the braces, plus 1, close it entirely. Alright, now this AF outside the braces gets multiplied with both the terms. That, let me do that simplification here itself so that I don't get confused and we do it correctly. Exactly, AF gets multiplied over here and that AF exists here also. Alright, so this one, so why the need of braces anymore? We don't have that anymore, we don't need that anymore. And here we have V naught over here and pulling this V naught by this to this side. So what do we have? V naught as it is. Alright, V naught as it is over there, and this is positive, dragging this side it will be minus V naught into S C2 R2 AF upon S square inside the brace, I mean S square R2 R3 C2 C3 plus S inside the braces R2 C2 plus R3 C3 plus R2 C3, close the braces, plus 1. Alright, so this one, this by this comes this side. Alright, no, this is still outside. Alright, don't get confused please, this is outside, it's not a part of the fraction. V naught minus this one, please don't get confused, it was a bigger one so it came out. V naught is outside the fraction. Alright, it's like this, it's like this, it's like this, please don't get confused. This is what, it's not a part of the transfer, I mean it's not the part of the ratio, that which equals AF V in upon this one. This repeats again because this is applicable for this one and this one individually, isn't it? S square R2 R3 C2 C3 plus S into R2 C2 plus R3 C3 plus R3 R2 C3 plus 1. Yeah, now taking out V naught as common from both the terms. V naught, we will have 1 over here in this place minus S C2 R2 AF upon entire term appears again. Alright, entire term. No, this is wrong, I'm sorry, this we have 1 minus V naught into S C2 R2, the gain, upon, this is applicable only for this one, isn't it? S square R2 R3 C2 C3 plus S into what is that, R2 C2 plus R3 C3 plus R3 C2 close the braces plus 1 in this term, which equals that one. That has to be written again, isn't it? AF Vn upon this entire term, S square R2 R3 C2 C3 plus S into R2 C2 plus R3 C3 plus R2 C3 close the braces plus 1. Here, this is the arrangement. Now simplifying this one, guys, I have confused from here. I'm taking back that one. V0 isn't the part of the fraction over here. Even it's not a part of the fraction over here. We have 1 minus this one. And taking out V0, I'm sorry, V0 has V0 taking out, we don't have this V0 over here. Please, I have confused you in 2 steps. Please make sure. Alright, V0 is taken out as common from both the terms, so this is the arrangement. Now that expression which is in the LHS, if we simplify this one, we'll have a V0 of this one. The LCM will be in the denominator. We have S square R2 R3 C2 C3 plus S times R2 C2 plus R3 C3 plus R3 C2 close the braces plus 1 will be the LCM. This, I mean, for this term this repeats, isn't it? In the sense S square R2 R3 C2 C3 plus S inside the braces will have R2 C2 plus R3 C3 plus R3 C2 close the braces plus 1. Alright, for this one, and the second half, like it's minus, this will be as it is, isn't it? S C2 R2 AF. So this will be for the LHS and this will be the RHS. No change in the RHS. That's the RHS. I cannot write this again. Why? Because one term gets cancelled here itself. Alright. So this will be the RHS. So a small change in the LHS, this one, and that will be the RHS as it is. So guys, this gets cancelled. This entire term on either side gets cancelled. We don't have that anymore. Alright. So this we don't have from the RHS, and this we don't have from the LHS. This we don't have from the LHS. See, the entire term has left over only with V0 and Vn, alright, which is equal to AF times Vn. So this one, we are searching for that ratio, V0 by Vn, V0 as it is, and this is dragged this side, so V0 by Vn, which equals it's AF, alright, it's AF. So we have AF upon we have this one, this comes down as it is, S square R2 R3 C2 C3 plus S, open the braces, R2 C2 plus R3 C3 plus R3 C2 close the braces plus 1. Guys, one thing can be done. We have a S term over here and the same S term that can be taken out. In the sense, we can extend this one. For S, taking out S as common, we have minus R2 C2 AF inside the braces, and then we can write down that plus 1. Alright, now this is the final transfer function of the transfer function which they asked for, standard transfer function of a second order low pass Butterworth filter. And usually the design procedure is for R2 R3 equal to R and C2 C3 equal to C. Plugging in this one over here, all right, or else yeah, we will make use of this one. Usually we go a filter is designed for these specifications, all right. So taking out R2, this one entire term is coming from all the terms, taking out this one, this one, which one, this part as common from all the terms. So what to do, like it's taking out R2, R3, C2, C3 as common from all the terms. S square alone is left over, and here we have that R2, R3, C2, C3, and even for this one we have 1 upon R2, R3, C2, C3 inside, close the braces. All right, so in a sense this can be rewritten for 1 upon R2, R3, C2, C3. all right guys. Now this is very much equal to that quadratic expression, standard second order transfer function. The denominator is very much equal to that one. Comparing this one with the s square plus 2 zeta omega n into s plus omega n square. All right, so comparing this one, s square, it's our s, and this will be omega n is over here, omega n square is this one, which gives us the expression for frequency of oscillations. All right, so this one very much, yeah, see this one, omega n, it's very much similar to omega n by, why? Because this is omega n over here, the same is repeated over here. This is omega n square. All right, 1 upon, now we'll have to, all right, so I made a small mistake, of course, comparing this with the standard expression itself. All right, I'm taking back that one. This has to be compared with, now what, with a R2 equal to R3 equal to R, and C2 equal to C3 equal to C. Plugging in this one, what do we have? This will be what do we have? This will be R into R square, C into C, C square. All right, and this will be, we don't have this anymore, like RC, 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 and here it will be RC, and even this will be RC. It will be no more like no 2 3, it will be C into C, R into R. All right, so guys, a small change over here, which equals RC as common from here. It's a 3 RC, isn't it? RC, it's a 3 RC. So here a small change over here, it's a 3 RC inside of 3 RC. All right, minus RC into AF. So we can take out even here we don't have that R and 2 and 3s. all right, so here this is the change with that one. RC as common from, no, it's a plus, I'm sorry, it's a bigger derivation, so I'm getting a little bit confused. It's plus as it is. Take out this RC as common. So what do we have here? Take out RC as common from these two terms. All right, so we have that RC. All right, so one combination of RC and one combination of RC gets cancelled. All right, and here it's S times 3 minus AF, S times 3 minus AF inside the braces, and it's a RC. Now this one, this will be like this will be R square, C square. Can you see? Now omega n square, this is very much similar to, okay, we have that AF gain, let it come out, AF, it's like omega n square upon S square plus 2 zeta omega n plus omega n square. So here comparing that one. All right, so what do we have? Omega n square upon S square plus 2 zeta omega n into S plus omega n square. Done. So we have this one, omega n square, this one, which gives the expression for frequency of oscillations, and zeta, which gives that condition to design the low pass filter. All right, we have, what do we have? Omega n square, which is equal to 1 upon R square C square. All right. So natural frequency omega n is the very higher cutoff frequency omega h square of a high pass filter. It's omega n, which is nothing but the omega h cutoff frequency, omega h, and from this one we have omega h is equal to 1 upon under root r c. All right, that one. And no, check this, it's from this one. All right, this is okay, but another important equation is we have to normalize. I'm taking back this one. All right, a little bit confusing with this one, but another important point is we have to normalize that transfer function to Butterworth response, so that we get the design expression. In that expression we say this has to be compared with s square plus root 2 s plus 1 Butterworth polynomials, in the sense to have this response, to have this Butterworth response, we expert says that this should be, what is that, 3 minus AF, that should be equal to root 2. In the sense AF 3 minus root 2 equal to AF, which is equal to 1.586, something like that. Alright, now what is this AF? We have considered initially it's nothing but 1 plus RF by R1, which is equal to 1.586, and from here itself we have RF by R1 equals what is that? 0.586, 1.5, this minus this one, so that will be left over. What it says, RF equal to 0.586 R1. So for as far as the designing part, we cannot consider whatever values we want according to this analysis. Like if the filter needs to give a Butterworth response like this one, we need to select this value. What it says, if we go for R1 equal to 10 kilo ohm, we need to, if we consider R1 to be 10 kilo ohm, RF should be equal to 10 times R1. It's 10 times 0.586, that is like 5.86 kilo ohms, like that. This should be the procedure. All right, so this is all.